In this lesson, we'll consider proofs involving the universal quantifier and the idea of proving statements for all x values in that universe. Often our main goal in most proofs is we want to prove statements of this form. For all values of x in this universe, p of x is true. Now, generally speaking, our universe is often too large to just try every single case. However, if we had a very small universe, if desired, we could potentially just check each number in the universe and make sure that p of x is true. But considering in most of the cases we've done the universe has been the real numbers, it's rather impossible to check each and every real number. What we do is we apply the principle of generalization. What the principle of generalization says is that if p of x can be shown to be true for an arbitrary x in the universe, then the statement for all x that's an element of u, p of x, is a true statement. What do I mean when I say arbitrary? Arbitrary basically means all you do is assume that it is a member of that universe. If that universe has certain properties for the whole universe and every element in it, you can assume those, but otherwise, absolutely no special properties can be used. We'll talk about these a little bit further as we go forward. Now, considering that we're going to be using the real numbers thoroughly, we need to pick up a few properties of the real numbers. And while these can be potentially proven or put into the definition of the real numbers, a good solid definition of the real numbers is not something that we will be discussing in a discrete math course. Generally speaking, this is reserved for a real analysis course. What we can do then is make a few assumptions about the real numbers that we're allowed to use. First off, the square of any real number is a non-negative number. Now, most of us probably take that for granted, that if you take a negative times a negative, you get a positive. And so when you square a negative number, you also get a positive number. But that has to be built into the definition of the real somewhere. Next, if you have an equation or an inequality, and you want to add a number to both sides, or for that matter subtract, you're welcome to do so. You can also multiply both sides of an equation by a non-zero number. And again, you're welcome to do so. Your equation will not change. You can multiply an inequality by a number, but we have to be a little bit careful there. If we multiply by a positive number, we'll get the same inequality. But if we multiply by a negative number, it actually reverses the inequality. And then finally, this last property is called the zero product property. The zero product property basically says that if you have a product of two expressions, say a times b is equal to 0, what that means is that either a could equal 0 or b could equal 0. But one of them at least has to be 0 in order for that product to be 0. Here's our first statement to prove. Again, the goal is we want to show this statement for an arbitrary value of x. And let me give you a little background on how this works. When you're writing a proof, you make a few assumptions that your reader knows a little bit of mathematics, some of the basic underlying structure. Your reader is going to know just as well as we will that x is going to be an arbitrary value. Let me show you how I would start this out. Let x be an element of the real numbers. Now, you could write in here that x is arbitrary, but when you write a proof, again, it is generally understood by your reader that when you say x is a real number, we're talking about an arbitrary real number. Now that we have that, we want to try to prove that x squared plus 1 is greater than 0. Again, we cannot assume any special properties. All we know is that x is some random real number, and that's it. But we do know some things about the real numbers that I showed you on the previous slide that you could assume. Because x is a real number, we can assume its square is non-negative. So here's what we'll write. Then x squared is greater than or equal to 0. Now what? We're getting kind of close to what we want, right? We've got that x squared is greater than or equal to 0, but I really want x squared plus 1. So let's add 1 to both sides of this inequality. Adding 1 to both sides, we get x squared plus 1 is greater than or equal to 1. Now basically some of the order properties of the real numbers are also fair to assume, and we know that 1 is greater than 0, right? Thus, x squared plus 1 is greater than 0. And that is the end of our proof. And again, after every good proof, you want to put some sort of marker that you're finished. And I like this black square. Let's go a little bit further. Suppose now we want to prove a conditional statement, the implication if you will. And the implication is of the form, for all x that's an element of the universe, we have p of x implies q of x. Now these type of statements come up very naturally in many applications. And when we do these, yes, we'll pick an arbitrary x, but the structure of p of x implies q of x is rather important here. We need to show that p of x implies q of x. And thinking about this by the sense of truth tables actually helps us. Remember that the statement p implies q is only false when you get true implies false. If you have false implies true or false implies false, remember we assumed that the implication p implies q was a true statement. What we really need to do is prove that true implies false does not happen. How do we do that? We'll assume that p is true, and then we'll show that under the case that p is true, it must be that q is true. Assume p, prove q. Here's our example. For all x in the real numbers, if x is less than -3, then x squared is greater than 9. Again, let's start off the same way. Let x be an element of the real numbers. And now what we'll do is we'll assume this property for p. And assume x is less than -3. Now, we have assumed p is true, and we want to prove that q is true. Somehow we have to prove that x squared is greater than 9. Remember, we have limited resources that we can use. All we really have is those properties of real numbers that I mentioned on the first slide. But we can work with them. One of the most important things about proofs is to always keep your eyes on where you're going. You want to show that x squared is greater than 9. So somehow we need x squared to manifest itself in our proof. Remember in the last example I added 1 to both sides of an inequality. This time let's multiply. Let's multiply both sides of this inequality by x. Multiplying both sides by x, we get x squared is greater than -3x. Now hold on, you might say. Why did you switch it to greater than? I just multiplied both sides by x, and in the process I flipped my inequality symbol from less than to greater than. Remember, when you multiply both sides of an inequality by a number, if that number is negative, you must flip your inequality sign. And how was it negative? Well, remember, x was less than -3. Now that we know that it's clearly negative, we should flip our inequality. But what now? We've got x squared is greater than -3x. Good! Let's see if we can get a 9 in the picture. We also want to have a 9 somewhere. Well, we've got a -3. If we were to multiply that by -3, we could get 9 like we want. So let's do another multiplication. Let's again multiply from the original inequality and see what we get. Instead, multiplying by -3, we get -3x is greater than 9. Now again, I multiplied by a negative number, so you'll notice that I've changed my inequality symbol again. We're actually really close to done. Take a look. We've got x squared is greater than -3x. We've also got -3x is greater than 9. -3x has x squared as a larger value, and -3x has 9 as a smaller value. It's the link in between the two, if you will. Officially, we call this property transitivity of an inequality, which is a property that we can assume. Putting these together, we'll get our answer that we're looking for. Putting this together, we get x squared is greater than 9, as desired. Let's review. Remember in the last lesson we talked about two different styles of proof, and so we're continuing our list today. How do you prove a statement of the form, for all x in the universe, p of x? Take a moment and think about it. How do you do it? Choose an arbitrary value of x in the universe and prove that p of x is true for that arbitrary x. Remember, as long as x is arbitrary, the principle of generalization can take us from showing that the statement is true for an arbitrary x and claiming that it's true for all x. Next question. How do you prove a statement of the form, for all x in the universe, p of x implies q of x? What do you think? For an arbitrary x in the universe, assume p of x is true and show that q of x is true.